Okay, prerequisite chapter, section 4, rational exponents and radicals. Okay, so our objectives for this section are going to be to learn about radicals, rational exponents, and rationalizing the denominator and putting in what we call standard form. So radicals. By now, I hope we know what a to the n means whenever n is an integer. So for instance, if we had, say, 3 to the power of 5, this means 3 times 3 times 3 times 3 times 3, right? 5 times. 1, 2, 3, 4, 5 times. 5 times. Right? It's a shortcut of multiplication. So now we would multiply these guys. So 9 times 9, we can group them up, right? So these guys right here is a 9. And then these two, well, that's another 9. And then this guy, well, he doesn't have a pair. Let's leave him alone. So 9 times 9, let's equal this. So 9 times 9 is 81 times 3. And so 81 times 3, let's see, that's 80 times 3, that's 240 times plus the 3 makes it 243. So 243, right? So that's what 3 to the power of 5 means. As another example, we could have 2 to the power of 5. 2 to the power of 5 is 2 times 2 times 2 times 2, 1, 2, 3, 4, 5 times 2. Five times. So that's, for example, let's group them up again. This could be a 4, and then this is another 4, and then there's another 2. And so this is 2 times, 4 times 4 is 16 times another 2. It'd be 16 times 2, which then becomes 32. So 2 to the power of 5 is 32. 2 is not that bad, so we could just multiply. You don't have to group them up this way. It's just something I like to do. But 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So either way, we get to that. Okay, so hopefully we're familiar with cases where we have some base number. Initially, we deal with nice whole numbers as a base. So 7 to the power of 2, that's 7 times 7, or 7 to the power of 3, that's 7 times 7 times 7, right? Okay, so we get the idea. Hopefully everything is fine when we have an integer value, right? Remember, integers are counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. There's also 0. If you remember, if we have a 0 there, 7 to the power of 0 is by definition a 1. Any number raised to the power of 0 is a 1. So for example, 3 to the power of 0 is also 1. And also 2 to the power of 0, that's also 1. Right? And then when we have negative counting numbers in the exponent, hopefully that is also familiar. If we had 5 to the power of negative 1, right? The negative in the exponent, the way we treat that is to rewrite it as 1 over 5 to the positive 1 power, or just in this case, it's just going to be 1/5. Good. If I had 5 to the negative 2 power, that would be 1 over 5 to the positive 2, which would then become 1 over 25. Good. Okay. So going back to say something like this, if we had 3 to the negative 5 power, this is equal to 1 over 3 to the positive 5 power, which then becomes, well, we already know that 3 to the 5th power is 243. So this becomes 1 over 243. Okay, so that's how we treat negatives in the exponent. That's a 0 always equals 1. And positive integer values. So hopefully all of this sounds familiar. And in this section, we want to think about something a little bit different. What if there's a fraction in the exponent, right? So what if we had 3 to the power of 3/4, for example? What do we do with that? All right, so To give meaning to a power such as 2 to the power of 4/5, whose exponent is a radical number, we need to discuss radicals. So the symbol, this symbol right here, this root, is the positive square root. Thus, the square root of a equals b means that b squared is equal to a, and that b is strictly greater than or equal to 0. Okay, so what in the world does this mean? So this kind of goes back to the idea that this notation symbol here is really sort of the reverse of multiplication when you're multiplying a number times itself, right? So we learn how to multiply. We learn our multiplication tables. 2 times 2 is 4. We learned that 3 times 3 is 9. We learned that 4 times 4 is 16, right? So we're multiplying. Whenever you learn a skill in math, usually there is the reverse skill. How do you undo that? How do we undo this process? And that's where this notation comes in, right? So you learn that the root of 4 is equal to 2. And the only reason why we know that is because we know our multiplication tables, right? We can't learn this without first learning multiplication tables. You have to do it in that order, and you have to know your multiplication tables well. Otherwise, you just won't know the answer, right? If someone just asks you what's the square root of 81 and you don't know your multiplication tables, then you don't have a way of knowing that. There's nothing we can do to the 81. We're not doing arithmetic to the 81 to get the answer. We're just using memory, right? We're just remembering what our multiplication tables tell us. So we know the answer is equal to 9 because we know that 9 squared equals 81, right? So that's what this thing is telling us. When you're given the root of a, the root of some number, the answer is b, if and only if it's true that b squared equals to a. Good? Okay, also notice that the answer here, the square root of a equals b, is positive, right? So it's the positive square root of. We always intentionally mean for this to mean the positive root, even though there is a negative b value that can also make this work. So, for example, note over here, note that negative 9 squared is also 81. So you might wonder, someone might ask, well, why isn't the answer to this negative 9? Well, it's not. By definition, we mean the positive root. If I wanted you to be negative 9, then we would have to put a negative on the outside, negative root 81, which would then be negative 9. Okay, so hopefully that's clear. Okay, square roots are special cases of nth roots. So the nth root of x is the number that, when raised to the nth power, gives you x. So, by default, when there's no other index in the root here, we mean it to be a 2. So if I ask you what's the square root of 25, by default, there's this little tiny 2 here, right? There's nothing there, then by default, there's a little 2 there, which means that we're looking for a number that such that when it multiplies by itself 2 times, the answer is 25. So in this case, the answer would be 5. The answer is 5 because 5 to the power of 2 is 25. Good. Okay, now on the other hand, if we had a cube root, so let's say we had the cube root of 8, the answer is 2 because we're looking for a number such that when you multiply by itself, this number of times, this index here, we get the 8. So this is an answer of 2, again, because we know our multiplication tables, and we know that 2 to the power of 3, right? So this little indice right there is going to be the same index that goes right there. 2 to the power of 3 is equal to 8. Is equal to 8. Okay, so in general, whatever index is here tells you the power you have to raise it to when this thing is being solved. So the principal nth root is defined as follows. the nth root of a equals b if and only if it's true that b raised to the nth power is equal to a. So if n is even, we must have a that is greater than 0 and b that's greater than or equal to 0. If n is odd, then we're allowed to have a negative, right? So here, for example, this is an odd index. N is 3. That's an odd number. So if we have a 3 there, we're allowed to have a negative 8 there. There is a number such that when you multiply by itself 3 times, the answer is negative 8. And in this case, that would be negative 2, right? And that's because negative 2 to the power of 3 equals negative 8. Okay, when we have an even index value there, so like let's say we had the fourth root of say 16. Now we're looking for a number such that when you multiply by itself 4 times, the answer is 16. And in this case, that would be a 2, and that's because, again, because we know our multiplication tables, we know that 2 raised to the power of 4 equals 16, right? Again, I'm not doing arithmetic to this. There's no special sauce here. I don't know how to find the answer other than recalling from my multiplication tables that 2 times 2 times 2, 4 times equals to 16. Either that or using technology, but that defeats the purpose, right? So technology should not be used in this case. All right, so note that what this thing is saying here is n is even, just like here. When it's even, then the a and the b both must be positive. So we cannot have a negative inside here, because if we had a negative inside here, if this was the fourth root of negative 16, a number such that when you multiply by itself 4 different times, the answer is negative, that wouldn't work, right? Because notice that negative 2 raised to the power of 4, well, that's negative 2 times negative 2 times negative 2 times negative 2. Well, negative times a negative equals a positive. This is equal to positive 4, and this is equal to, again, positive 4. So the whole thing equals to 16. That's not negative 16. So when we have an even index in the root, this value inside here must be positive, and the answer must be positive. On the other hand, if we have an odd index here, this value, this little n value is odd, for example here, if we have an odd one, we're allowed to, we don't have to, but we're allowed to have a negative inside the root, and then the answer will also be a negative number. Good? It could also be positive, such as in this case. All right, moving on. Okay, so properties of roots, properties of nth roots. So here are several properties that we can look at. If we have the nth root of a times b, this first one, property 1, tells us that if we have one big happy root with an a times b, a multiplication, notice that's a multiplication, inside the root, then we can say that that's equal to the multiplication of 2 separate radicals, the nth root of a times the nth root of b. You can go forwards or backwards with this, so you can start here and say, well, that equals to that, or you can start there and say, well, that equals to that. Sometimes one thing might be useful or the other. So for example, notice here that if we have the cube root, the third root of a multiplication of negative 8 times 27, then according to this property, we can separate that into 2 separate roots, the cube root of negative 8 and the cube root of 27. The cube root of negative 8 is negative 2, right? And that's because, note, negative 2 times negative 2 times negative 2 equals to negative 8, right? So that's how I know that this has an answer of negative 2. And the cube root of 27 is 3, again, because I know that 3 times 3 times 3 equals 27. 3 times 3 is 9, times 3 is 27. So that's how I know that this results in a negative 2, and this results in a 3, and now negative 2 times 3 is negative 6. Okay. The next property is if we have a fraction inside the nth root, then this property tells us that we can separate it into a fraction where the numerator has an nth root of a and the denominator has an nth root of b. Right? So we keep the same order of a and b in the numerator and denominator. So this is kind of a subtle difference. Here we have a fraction inside the nth root, whereas this is a fraction where there's an nth root of a in the numerator and an nth root of b in the denominator. Again, we can go forwards or backwards with this process. Sometimes one form is more useful than the other, so it's good to be able to go back and forth. So as an example, here we have the fourth root of 16 divided by 81. According to this property, this is equal to the fourth root of 16 divided by the fourth root of 81. The fourth root of 16 is 2. Again, recalling our multiplication tables, 2 times 2 times 2 times 2, 4 different times, 1, 2, 3, 4, is equal to 16. And the fourth root of 81 is 3. Again, recalling my multiplication tables, that is because 3 times 3 times 3 times 3, that is also equal to 81. That's how I know that the fourth root of 16 is a 2. And the fourth root of 81 is a 3. Okay, the next property, property number 3. If we have an nth root of a inside the mth root of m, this is equivalent to the m times n root of a. So we have an index of n right in here and then an index of m. So we multiply both of those indices in order to get this answer right here. Expanding on number 3 a little bit, you can arrive at it this way. Let's say I'm just going to copy it down here. We have the nth root of a, and then all of that is in the mth root, right? So now this, using our fractional exponent notation, this is equal to a to the power of 1 over n, right? The nth root of a is the same thing as a to the 1 over n. Hopefully that's something you've learned in the past. And then we can do the same thing with this mth root. So now this is a to the 1 over n, and then the whole thing is being raised to the 1 over m. We know with exponents that if we have an exponential number raised to another exponent, we multiply the exponents. So this is equal to a to the 1 over n times 1 over m, which then is just multiplication, right? So this is equal to a to the 1 over m n. The order doesn't matter. Well, let me put it back the way it was. M n times m. Good. And then going back to our notation, a fractional exponent, well, this is equal to the root of, and then m times n here. That looks ugly. And then this is the index is m times n, right? Which is what that's saying. Good. Okay, so for example, notice that in here we have the square root. By default, if there's nothing there, that means that there's a little 2 there. So that's the square root of the cube root of 729. So this is equivalent to the 6th root of 729. Now, how do we arrive at this number 3? Again, just because we know our multiplication tables. So we can say that this is the answer is 3 because we know that 3 times 3 times 3 times 3 times 3, 1, 2, 3, 4, 5, 6 of them is equal to 729. Okay, so for something as big as this, maybe technology is useful, a calculator is useful, table is useful, something. So this simplification process of knowing that the 6th root of 729 is 3, I wouldn't expect you to just know that off the top of your head. I would expect you to be able to do simple ones, small numbers. The larger ones, conceptually, you should understand what's happening, but then if you need to use technology to find the answer to these larger ones, then I think that would be reasonable. Okay, just understanding what it means is what's important. Okay, so now the next property. The nth root of a to the n is equal to a, right? So this is kind of saying these two things kind of undo each other. If I have, let's come over here. If I have the third root of 2 to the third power, right? 2 to the third power is 8. The cube root of 8, well, it's 2. So you can also say that these two things kind of undo each other. You can also say that this is 2 to the third power, and then the whole thing is raised to the 1 over 3 power, which is equal to 2 to the third power times 1 over 3 power. This becomes 2 to the first power, which is just going to become 2, right? So we can kind of think that this index, the nth root, in this case being a 3, and this power undo each other, and the answer is just going to be whatever is there. Okay, this is only true if the index is odd. If it's odd, they kind of undo each other, because it's true whether this base number of 2, whether it's positive or negative, it'll keep it. It'll always keep it. So for example, if we had instead of 2 to the third power, what if I had negative 2 to the third power, and I want to find the cube root. The cube root of negative 2 to the third power, this also works. This becomes it's the same thing as the cube root of negative 8. And we know the cube root of negative 8 is negative 2. So it works. The 3 in the index of the root and the 3 in the exponent of negative 2 just give you that the answer is going to be negative 2. Notice that that's not true when we have an even one. Property number 5. So for example, if I had the fourth root of 2 to the fourth power, in this case, the answer is going to be 2. Because, well, let's simplify it a little bit. This becomes 2 to the fourth power is 16. So that would be 16. We have the fourth root of 16. And the fourth root of 16 is 2. And that's because 2 times 2 times 2 times 2 4 times equals to 16. So it kind of works out. So when they're positive, it works out. But notice that when it's negative, it doesn't work out. If I have negative 2 raised to the fourth power, and then I want to find the fourth root of that, now it doesn't quite work out, because now negative 2 to the fourth power is still positive 16. And I want to find the fourth root of that. The answer is 2. So what you want to point out is that here I started with a positive 2, and the answer was positive 2. Here I started with a negative 2, and the answer was positive 2. So when the index n is an even number, it always gives you this value, but positive. If it's positive, it keeps it positive. If it's negative, it makes it positive. And that is the same property as an absolute value. Right? So that's a very important property in math. These two things mean the same thing. Right? So here, look at our example. The fourth root of negative 3 to the fourth power. Negative 3 to the fourth power, that's going to be equal to multiplying negative 3 times negative 3, negative 3 times negative 3 times negative 3 times negative 3, 4 times. 1, 2, 3, 4. There are 4 negative numbers being multiplied, so that means that the answer is going to be positive, right? These two become positive 9. These two become positive 9. So the whole thing becomes 81, right? So this is the same thing as asking you the fourth root of 81, and the fourth root of 81 is positive 3. Good. So notice that what we did is we started with a negative 3, and if you were just thinking, oh, these two things cancel each other, you might think that the answer is negative 3, but it's not. The answer is positive 3, right? It turned it positive. If we had started with an actual positive 3, then this process would have also given us 3, right? So that's what the absolute value function does for us. If we have a positive number, it keeps it positive. If we start with a negative number, it makes it positive. So that's what this is doing. On the other hand, if it's odd, like this example, again, we have a cube root there and a power of 3 there. So negative 5 to the power of 3, that's negative 5 times negative 5 times negative 5. That's negative 5 times negative 5 times negative 5. Well, that's equal to negative 125. 5 times negative 5 makes it positive 25. Positive 25 times negative 5 then equals to negative 125. And now if I want to find the cube root of negative 125, the cube root of negative 125, then that's just going to be equal to negative 5. So in this case, it kept it. We started with a negative, we ended up with the exact same value. If we start with a positive, like 2 to the 5th power, the answer is going to be 2. So when the index is odd, we just keep whatever number is in there. When the index is even, we keep whatever number is in there, but make sure it's positive. In other words, we apply an absolute value function to whatever number is in there. Okay, so that's what that means. So let's look at this example. The cube root of x to the power of 4. How do we simplify that? All right, so what we want to do is think about separating these things. Well, there's a couple of ways that you could do it. One way to do it is to separate this as the cube root of x to the 3rd power times x to the 1st power, right? When we are multiplying two exponential numbers with the same base, we add the exponents. So if I wanted to simplify this, it would be x to the power of 3 plus 1, or 4. And the reason I separated this way is because now we know that we can separate this as the cube root of x to the 3rd times the cube root of x to the 1st. And now the cube root of x to the 3rd power, now they undo each other, right? And they're both odd, so that means that it's always whatever this is. That's just going to be x. Now remember, x could be positive or negative, we don't know, but whatever it is, we keep it. Good. And then over here, we end up with, well, there's no way to simplify that any further, so we can just leave it as the cube root of x. All right, let's try a different one. All right, let's try this one. Again, I want to try it in a couple of different ways. Let's try, first of all, simplifying the 81. So the 81, I'm going to do a little tree over here. 81, well, we know that 9 times 9 is 81. And we know that 3 times 3 is 9, and we know that 3 times 3 is 9. So that means that 3 times 3 times 3 times 3, 4 of them equals 81. So 81 wasn't so bad, but sometimes they get kind of large, and a nice little tree like this can help me figure it out. So 81 is really equal to 3 to the power of 4. Okay, so I'm going to come over here, and I'm going to say that this is the same thing as the 4th root of 3 to the power of 4, x to the power of 8, and y to the power of 4. Again, there's a couple of different ways that you can do this, but I'm going to go ahead and separate this guy in here into two different terms. It'd be 3 to the power of 4. I'm going to separate x to the 4th power times x to the 4th power times y to the 4th power, and then the root of that. The reason I chose to do that is because I can see that the index here is 4, so it works out nicely if I have little groupings with powers 4 like I do now. Good. So now I know that I can separate this into the 4th root of 3 to the 4th power times the 4th root of x to the 4th power times the 4th root of x to the 4th power times the 4th root of y to the 4th power. Good. And now in each of these cases, they kind of undo each other. So here they undo each other to give you a 3. Good. And now here we have a little issue because, again, I don't know if x is positive or negative. If x was a positive number, if I knew for a fact, if x was known to be strictly greater than or equal to 0, then this would just be x, right? Like if this was a 5 right in here, 5 to the 4th power, the 4th root, okay, the answer would just be 5. But I don't know what x is, and what if it's negative? So we have to make sure to deal with it by saying it's the absolute value of x. Right, raising x to the power of 4 is going to make it positive, and then the 4th root of that value is going to be positive, so it just guarantees that. Good. Times, now this, again, it's going to happen. We have x right here, and this is going to give you the absolute value of x, and this is going to give you the absolute value of y. Okay, so if x turned out to be a positive number and we go through this process. This process would make it positive. So this can be simplified as x to the second power. So this is equal to 3x to the second power, right? I no longer have to deal with the absolute values because there's two of them, and I know that this is going to make it positive anyway. So if x was negative, squaring it would make it positive. So I'd still get the same answer as this. Now the y does have to stay inside its absolute value because I don't know what y is, and I know that this process is going to make it positive. Okay, all right, let's look at your solutions from your author. Okay, so that's what your author's solutions are, same thing. And they left it in the same format. Okay, separating it. Okay, they did it slightly differently here, where they rewrote it this way. Okay, that's a nice little shortcut as well. Either way will work. Okay, here's another example. Combining radicals. Okay, so we can combine radicals as long as they are the exact same root. Okay, so we're going to start off by simplifying each one. Again, I'm going to create a little tree for each of these. The 32, I know that's a 2. 2 goes into that. 2 goes into that 16 times, and 2 goes into that 8 times, and 2 goes into that 4 times, and 2 goes into that 2 times. So, as you might already know, 32 is equal to 2 times 2 times 2 times 2 times 2, 5 times, right? So 2 to the power of 5, 1, 2, 3, 4, 5, is equal to 32. Now 200. So let's create a little Ch0 over here for 200. Okay, so that's 2 times 100, 2 times 50, 2 times 25, and 5 times 5. Okay, so then this tells me that if I multiply 2 times 2 times 2 3 times, times 5, I end up with 200. So 2 to the power of 3 times 5 to the power of 2 equals 200. Okay, so now I'm ready to come back over here and say that this 32, well, that's equal to 2 to the power of 5, and it's the square root of that. Remember, this is 32, plus, and now the square root of 2 to the power of 3 times 5 to the power of 2. Okay, so just like before, I'm going to simplify by grouping them by powers of 2. And the reason I'm doing powers of 2 is because this invisible number out here is going to be a 2, right? By default, if there's nothing there, then we know that there must be a little 2 there. This is a square root. Okay, so I'm going to rewrite this as 2 there of 2 to the second power times square root of 2, 2 to the second power there, times the square root of 2. Right, and again, I'm just going to put a little 2 there and a little put 2 there. It's a lot of 2's going on. So let me highlight them. These are the 2's that represent the index of the root, and they're really messy there, right? So by default, if there's nothing there, we know it's a 2, so I'm just going to go ahead and erase them. It's messy looking. Okay. So now these undo each other. And they're even, 2 and 2, but in this case, it's not a mystery. I know that this 2 right here, I know that this is a positive number, so I don't have to worry about absolute values. The absolute value is going to happen if I know it's negative, or if I don't know what it is, if it's an independent, if it's a variable. But I know it's a 2. A 2 is positive, so I don't have to worry about that. The answer is just going to be 2. So this gives me a 2, right? Or the square root of 4, same thing. Square root of 4, okay, so that's going to be 2. Times, well, there's nothing we can do there, so let's just leave that as a 2. So this leads to 4 root 2. Good, okay. Plus, this side, again, I'm going to group them up in powers of 2, so this is going to be equal to the square root of 2 to the second power times the square root of 2 to the first power. There I've used up 3 of them, times the square root of 5 to the second power. So this is going to be a 2 times root 2 times 5. So this becomes plus 10 root 2. And now you can look at it in a couple of different ways, but I like to think of it as 4 copies of root 2 plus 10 copies of root 2, right? So they both have the exact same root, so we can just go ahead and add this number. 4 copies of root 2 plus 10 copies of root 2 will give us exactly 14 copies of root 2. Okay, so you don't have to break it down quite like I did. I'm just breaking it down into a lot of little steps just to make sure people can follow what I'm doing. But there's some natural shortcuts that people can take, especially when the numbers are really easy, like 2 to the power of 5. You just want to break that down as square root of 4 times the square root of 4 times 2. That's fine too. So there's a variety of different shortcut notations that people can take. Feel free to do that as long as you put down enough work for someone to reasonably follow what you're doing. Remember, our goal is not just to find answers. Anybody can find answers. We have calculators for all this. The goal is to explain why that's the answer, so someone should be able to follow your work and reasonably conclude what the correct answer should be. All right, example number 2, combining radicals. So if we had, well, note it says if b is strictly greater than 0, then, all right, so they're giving us information. B is definitely a positive number. All right, so the square root of 25b minus the square root of b cubed. Okay, so let's simplify that. In this case, we know that b is definitely positive. So this will end up being 5 to the power of 2. The square root of 25 is 5. So this is just going to become, this guy is just going to become 5 root b minus, and now this guy, again, we can regroup it as the square root of b squared times the square root of b, the power of 1. And here we are taking a number, we're squaring it, and then we're taking the square root. So this is a case where this index and this undo each other. And because we know b is definitely positive, then we know that this is just going to be equal to b. Good. If this was not here, if this was not given to us, then right now we would have to conclude that this is the absolute value of b. Right? Make it positive. Start with some number, square it, get the square root of it. That makes it the absolute value of b, and we don't know if b is positive or negative. But because we do know that, they gave us this value here, then we could say that this is just going to be equal to just b. B. Okay? All right, so this is equal to 5 root b minus b root b. And again, we can combine these things. We have 5 copies of root b minus b copies of root b. So we have 5 minus b copies of root b. You can also think of this as factoring. So this and this term are alike. Let's highlight them. This term and this term are alike, so I'm going to factor it. So I'm going to rewrite it as 5 minus b, parentheses, and I'm factoring out this root b, right? It's like the reverse of distribution. We're used to distributing where we take a term and we multiply each term by it. So 5 times root b is 5 root b minus root b times b is equal to b root b. Right? So it's kind of like the reverse of distribution, factoring. And that's about as much as we can do, right? So there's our final answer. Okay, let's see what your author has as a solution for these guys. So similar, except, there's more than one way to solve these. So your author recombined the 32 instead of factoring all the way down to 2 to the power of 5 like I did. Your author just wrote it as 16 times 2. Clever. Root of 16 is going to be 4. So this becomes 4 root 2. It's the same answer that we get. It's just a different path. If you see it, then great. If you see a nice large even square, then this works out well too. Either way, we get to 14 root 2. And over here, same thing. We get 5 root b minus b root b, just like before. And so we end up with this. Okay, another example. The square root of 49x squared plus 49. So remember that we do not have a property that lets us separate a radical when there's an addition or a subtraction. So very, very common mistake is for people to think that this is equal to the square root of 49x squared plus the square root of 49. So then they go, okay, well, this is just going to be 7x plus 7, right? And that's not true because this is not allowed. You're not allowed to do that. Right? We cannot separate by an addition or subtraction this way. We only know we can do that when there's multiplication. So the only way to simplify this is to turn it into a multiplication by figuring out what we can factor, what they have in common, then separating them using our root property of multiplications. So let's get rid of all of this. Okay, so obviously 49 is the common term inside here. So this is going to be equal to 49, parentheses, x squared plus 1. Remember, this is, again, the reverse of distribution. 49 times x squared is 49x squared. 49 times 1 is 49. All of this lives inside this this square root. And now we have multiplication. 49 times x squared plus 1. So this is equal to the square root of 49 times the square root of x squared plus 1. Good. Now this we cannot simplify any further. We're done there. Again, you cannot separate by addition. So this is not equal to the square root of x squared plus the square root of 1. But this we can simplify as a 7. 7 times 7 is 49. It's the square root. So this is 7 times the square root of x squared plus 1. And again, that's as good as it gets. That's as far as we can go. So really, we were only able to simplify by factoring out the common 49 and realizing that that can be factored as a 7. And then there's no way to simplify this any further. Okay, let's see what your author did. Same thing. Okay, rational exponents. As I mentioned earlier in this video, we can have fractional exponents of the form 1 over n. So to define what it means by a rational exponent, equivalently a fractional exponent such as a to the 1/3 power, we need to use radicals. To give the meaning to the symbol a to the 1 over n in a way that is consistent with the laws of exponents, we should have that the following is true, right? So this is just paying attention to something I mentioned briefly earlier, that we know that when we have exponential powers, the properties of exponentials tell us that if we have x to the 2nd power, and then this is being raised to the 3rd power, this means it's x squared times x squared times x squared, right? 3 times. X squared times x squared times x squared, which is the same thing as x to the power of 2 plus 2 plus 2. If we have exponential numbers being multiplied with the same base, we add the exponents. So there are a total of x to the power of 6. Likewise, you can also kind of expand this. There's 2 copies of x here, 2 copies of x here, 2 copies of x there. In total, there are 6 copies of x. So our rule is that x to the 2nd power raised to the 3rd power, an exponential number raised to another exponent, is the same thing as multiplying those 2 exponents, which gives us x to the 6th power. So hopefully that sounds familiar. And so that's what they're saying here, that if we're going to be dealing with a fractional exponent, if we're going to kind of define what that means, we have to be consistent with this rule. So they're pointing out that if I have, say, for example, 2 to the power of 1/3, we're trying to figure out what that is, then it must be true that when I take 2 to the power of 1/3 and then we raise that to the power of 3, because of this property, this must be equal to 2 to the power of 1/3 times 3 which is equal to 2 to the power of 1, since 1/3 times 3 is 1, which is just equal to 2. So 2 to the 1/3, what that means, 2 to the 1/3 is a number such that when you multiply it by itself 3 times, the answer is 2. Good. Okay, well, if you think about what that means, well, that's exactly what the cube root of 2 is. The cube root of 2, this represents some answer, some decimal, so that when you multiply it by itself 3 times, the answer is going to be 2, right? If we have this, then we know that the cube root of 2 times the cube root of 2 times the cube root of 2, that these three things, well, they just multiply to give you a 2. Good. And so that's how we're connecting that 2 to the 1/3 power is equivalent to the cube root of 2. Right? This must be the same as this. They both accomplish the same thing. The cube root of 2 is a number such that when you multiply by itself 3 times, the answer is 2, and that's what this is. Right? We can also expand on this a little bit, knowing our properties that we have now. Right? We can also say that this thing is the same thing as the cube root of 2 times 2 times 2. Since we have 3 different roots being multiplied together, we can bring it all under one big happy root, which then gives you the cube root of 8, or 2 to the 3rd power, which is then equal to 2. Right? So any way you look at it, this gives you a 2, and that's what this is describing right here. Okay, so that's what this is saying. A to the power of 1 over n raised to the nth power, because of this property of exponents, must be the same thing as a to the 1 over n times n. The 1 over n times n becomes 1, which means it equals to a. So that's defining this. Both of these give you the same result. So a to the 1 over n is the same thing as the nth root of a. So for example, 3 to the 1 over 4 power is the same thing as the 4th root of 3. You can go back and forth between these. Sometimes this notation is useful. Sometimes this notation is useful. So you can go back and forth between these and simplify whatever problem you're in. So in general, we define rational exponents as follows. So definition of rational exponents. For any rational exponent of the form m over n in lowest terms, where m and n are integers and n is strictly greater than 0, we define the following. So a to the m over n is equivalent to the nth root of a raised to the power of m. Or equivalently, a to the m over n is equivalent to the nth root of a to the m power. If n is even, then we require that a be positive. All right, what in the world is this saying? So this is saying that if we have, okay, so back to the previous one, if we had 5 to the power of 1/3, this is the same thing as saying the cube root of 5, right? If we have 1/3 there. This is a decimal value such that if we multiply it by itself 3 times, the answer is 5, right? Both of these express the same thing. That's when we had a 1 there. So what if we had a 5 and then we had a fractional value of, say, 2/3, right? What do we do with 2/3? Well, this is saying that we can do one of two things with this. It comes in 2 flavors. We can say that this is the same thing as the cube root of 5 raised to the power of 2, or if it suits you, whichever you like, you can also say that this is equal to 5 to the 2nd power and then inside the cube root. Good? Either one, whatever works best will work, is fine. So they're both equivalent. That's why there's two versions of this. Good. All right, let's do some examples. All right, so some examples. Okay, so let's say we have a to the 1/3 power times a to the 7/3 power. We know from before, from exponential properties, that if we have two exponential numbers with the same base being multiplied, what we do is we add the exponents. Okay, so this is equivalent to a to the power of 1/3 plus 7/3. We add the exponents, so now we have a little addition of fractions happening in the exponent. This is a to the power of 1/3 plus 7/3. They already have the same denominator, luckily. That's just a really easy answer. That just becomes this fraction with 1 plus 7 over 3, which becomes a to the 8/3. Good. And again, we have two different ways to express the same thing. Obviously, this is a perfectly good answer right there. Or we can also say that this is equivalent to the cube root of a, and then the whole thing being raised to the power of 8. Or you can also say, no, this is actually a to the 8th power, and then the whole thing is inside this cube, right? That's also true. And then we can simplify each of these a little bit more. So this one, for instance, we know that if we have 3 of these, we can separate it into powers of 3 and simplify. This is a to the 3rd power inside the cube root times cube root a to the 3rd power. I've used up 6 of those a's. Times the cube root of a to the 2nd power. So 3, 6, and 2 makes it 8. And then here we say that these two kind of undo each other. So this becomes an a from there times an a from there times, and then, well, there's nothing we can really do with this one, so this becomes the cube root of a squared. So we end up with a squared cube root of a squared. That's one way to simplify it. Okay, this one, on the other hand, to simplify it, this is saying that there are 8 copies of this. So we have cube root of a times cube root of a times the cube root of a. Okay, and then there's going to be 8 of them. 8 times, right? But if we have 3 of them being multiplied, then that just gives you an a, right? Because that's what this means. The cube root of a means that it represents a value such that when you multiply it by itself 3 times, the answer is a. So the first 3 of these will just give me an a. So this will result in a multiplication of 8 items, where the first 3 result in an a, the next 3 result in another a, and then finally we'll end up with 2 of these that do not group up anyway. And so we end up with the same thing as this. A squared and then cube root of a squared. One more way to look at this, let's come back over here, is a to the 8/3 power. We can also turn this into a mixed number, sorry. So this becomes a to the power of 2 and 2/3, right? That's as a mixed number. Mixed number, right? So there's 2 whole copies and then 2/3 copies. So this is the same thing as, a to the 2nd power times a to the 2/3 power, which once again gets us back to the same thing, a to the 2nd power, and then the cube root of a squared. So any way you slice it, we end up with the same answer there, or there, or there, depending on which path you take. All paths lead to the same thing. Some paths sometimes are a little easier than others, depending on what you're working with, but they all give you the same thing at the end of the day. Can we go any further than that? Not really. Remember that in order for an a to come out, we need a to the 3rd power, and it's stuck as an a squared, so there's no way to simplify that any further. Okay, Another example. A to the 2/5 power times a to the 7/5 power divided by a to the 3/2 power. Okay, so we know that when we multiply exponents, we add exponential numbers, we add the exponents. And when we divide exponential numbers, we subtract the exponents in this order. Hopefully that looks familiar. So what we have to do here is take this a to the 2/5 power plus 7/5 divided by a to the 3/5 power. Now here, luckily, they already have the same denominator, so this will be equal to 9/5, a to the 9/5 power divided by a to the 3/5 power, which then becomes a to the 9/5 power minus 3/5. Right? Again, if we have exponential numbers being divided in this order with the same base, in this case the a, then we subtract the exponents, which then gives us a to the 9 minus 3 is 6/5. Okay, so now it's just a matter of simplifying that. A to the 6/5 power. As a mixed number, we can say that that's equal to a to the 1 1/5. Again, as a mixed number. Mixed number. So then this gives us a to the 1st power times a to the 1/5 power, which becomes a times the 5th root of a. So that's the answer there. And we can arrive at it in a couple of other ways as well. We can also think of this as the 6th root of a, the 5th root of a to the 6th. The 5th root of a to the 6th, which then becomes the 5th root of a to the 5th times the 5th root of a to the 1st. And so these two undo each other. Notice that it's an odd indice, so they just truly undo each other. Whatever the value of a is, whether it's positive or negative, we'll get the same answer, a. So this becomes a, and this becomes the 5th root of a, same as before, same answer as before. Okay. Another example. So if we have 2 times a to the 3rd, b to the 4th, the whole thing is being raised to the power of 3 to the 2nd power. So we can use these properties. We know that if we have multiplication and we're raising a product, a times b times c to the power of n, then we can kind of distribute the exponent and have a to the n, b to the n, c to the n. And we've already dealt with this property before. So this is equivalent to, okay, so 2 has a 1 there. By default, it's a little invisible 1 right there. Little 1 right there. So this is going to be 2 to the power of 3/2 times a to the 3rd power times, how do I do this? I'm going to rewrite it like this, to the 3/2 times b to the 4th raised to the power of 3/2. Right, so this one, let me come back over here actually. Let's rewrite it as to the power of 1, and then this is being raised to the power of 3/2. Okay, so it's kind of like a distribution. I'm going to take each one of these terms and raise it to the power of 3/2, which in the first term, in the first case, that just becomes 2 to the power of 3/2. In the second case, then we have a to the power of 3 times 3/2 times, and then in the fourth case here, we have b to the power of 4 times 3/2. So this becomes 2 to the power of 3/2 times a to the power of 9/2 times b to the power of 12/2. This one simplifies as just 6, so that's easy. These are a little more complicated. Again, we can do it in a couple of different ways. Mixed numbers are good. As a mixed number, this would be 1.5. Right? If we're going to go with a mixed number method, this becomes 2 to the power of 1 1/2 as a mixed number. a to the power of 2 goes into 2 goes into 9 4 times, so 4.5 times as a mixed number. And then b to the power of 6, since 2 goes into 12 6 times. So this is just going to become equal to 2.5, so 2 root 2 times a to the 4th power root a times b to the 6th power. Good. So then separating them and regrouping them, we would end up with a 2a to the 4th power b to the 6th power square root of 2a. Good. Okay, again, if you're happy with that, great. And again, we did that by going to mixed numbers, right? So these are all mixed numbers, mixed fractional values, mixed numbers, there and there. Or, right, another way you could do this, well, this way, equals, we can think of the root, so go back to the root. This is the square root of 2 to the 3rd power times the square root of a to the 9th power times the square root of b to the 12th power. And again, they come out in groups of 2, so only one pair of 2's can come out from here. So we have a 2 and then a root 2, right? That's a shortcut. That's just the way I like to think about it, in terms of, or instead of rewriting it as the square root of 2 squared times the square root of 2. Right? Times, okay, and now this guy here, that's going to be, now we have to be careful here because, okay, I'm going to do the slightly longer way of regrouping them. This is the square root of a squared times the square root of a squared times, I've used 2 of them, the square root of a squared, 3 of them, the square root of a squared. So far I've used up, I had 9 of them, and I've used 2, 4, 6, 8 of them. There's only 1 remaining. So then now there's the square root of a, the power of 1, right? So that's 2, 4, 6, 8, and the 1 makes it a 9. So that's all 9 of them. Okay, and now here, remember, we don't know the value of a. A could be positive or a could be negative. So if you're thinking to yourself, well, they just kind of undo each other. If we square a number and square root it, the answer is just going to be a. Well, you could be wrong. You have to be careful, because if a is negative, then this is no longer true, right? Like if a was a -3, then this process would give you +3. So this results in an absolute value of a. 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 And, well, this doesn't simplify, so we just leave it as the square root of a. Good. So now the absolute value of a times the absolute value of a times the absolute value of a, this is going to guarantee that the answer is positive, right? Because there's 4 of them. These 2 multiply to give you a positive number. So whether a was positive or negative, a to the 4th power is going to be positive. So this just becomes a to the power of 4. Right? The fact that there is an even exponent there guarantees that the answer to this is going to be positive, so we no longer need the absolute values. Right? It's redundant to do that, because a to the 4th is already positive. We don't need to bring it together and wrap it inside absolute values. Good. If there were only 3 of them, then we would have to continue to leave the absolute values to guarantee that our answer is positive. Good. Okay, hopefully that makes sense. And so bringing this down, we still have 2 root 2 from there. And no, here we don't have to deal with absolute values since we know 2 is positive, right? Here we have to deal with it because we don't really know what a is. Same thing with this, the square root of b to the 12th power. that's going to result in, just like over here, 6 copies of the square root of b squared, and that results in the absolute value of b. But we're going to have 6 of them. And again, 6 of them means that they're going to be even. So that's why this just simplifies to b to the 6th power. Okay, so this one resulted in that guy, this guy 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 resulted in that guy. 1, 2, 3, 4, 5, 6. Oh, I did too many. 1, 2, 3, 4, 5, 6. Okay, so this absolute value times this absolute value, when I multiply the two values, I know it's going to be a positive b squared, and b squared is always positive, so it just makes sense that all of this is just going to be b to the power of 6. Okay, all right, so our final result then is 2 square root of 2, a to the 4th, square root of a, b to the 6th, ending in the same answer as before, 2a to the 4th, b to the 6th, square root of 2 times a. Okay, same answer as before. Whichever one makes most sense is the best way to do it. And again, you don't have to do as much detail as I did. I'm just flushing out those tiny little details. Hopefully it's making sense. So this is what your author did. Oh, your author did not reduce them. Okay, using the laws of exponents with rational exponents. Okay, so let's simplify this. So we have a fraction here. The numerator and denominator have exponential values with fractional exponents, and then the whole thing is being raised to a power. So let's simplify this. This 3 then becomes 2 to the power of 3, x to the 3/4 times 3, divided by y to the 1/3 times 3. Okay, and then the other fraction is y to the 4th power divided by x to the negative 1/2 power. So this becomes 2 to the 3rd power x to the 9/4 power divided by y to the 1st power, or just y, since 1/3 times 3 cancel out. And 3/4 times 3 becomes 9/4, times y to the 4th power divided by x to the negative 1/2 power. Good. Okay, so now the 2 to the 3rd power, we don't really do anything with that. I'm going to group these up this way. This is the same thing as x to the 9/4 power divided by x to the negative 1/2 power. Remember, we can do that because everything's being multiplied. We don't have to worry about common denominators or anything like that. Times, and then we have y to the 4th power divided by y to the 1st power. So this then becomes, let's put it over here, equals 2 to the 3rd power times x to the 9/4 power minus negative 1/2. Right? That's how we deal with a subtraction, a division like this, a fraction. We take the exponent in the numerator and subtract it from whatever's in the denominator. Times, and then this becomes y to the 4 minus 1. Almost there. This is 2 to the 3rd power, x to the, and then we have a subtraction of a negative that turns it into a positive, 9/4 plus 1/2. Times y to the 3rd power, 4 minus 1 is just 3. Here's the first time we run into this situation. We have a little addition of fractions in the exponent, but up to now we've always had common denominators already given to us. So this is the first time we're going to have to manipulate this a little bit. So I'm going to have to get a common denominator with just 4. So I'm going to multiply this by 2 over 2 to give me a 4. And now I'll end up with 2 to the 3rd power times x to the power of 9/4 plus 2/4 times y to the 3rd power. Almost there. 2 to the third power, x to the 11/4 power times y to the third power. And again, depends on how you like to look at it. We can think of this as the 4th root of x to the 11th, right? And then to come out of that 4th root, we need little groups of 4. So we can think of this as the 4th root of x to the 11. There's 11 copies of x being multiplied. 4 of them come out to give you an absolute value of x, again, because it's even and because we don't know anything about whether x is positive or negative. So the groupings are going to be this way. I'm going to separate it as 4, and that's x to the 4th, x to the 4th. That takes care of 8 of them, and then x to the 3rd. These are going to give you one absolute value of x and then another absolute value of x, which means we don't need the absolute value anymore. Good. So this will become absolute value of x times absolute value of x times the 4th root of x to the 3rd power. Doesn't simplify any further than that. And then these two, again, are x squared, right? And so this gives you x squared, right? The answer to x squared is positive, which means we don't have to worry about the absolute value anymore. Good. Okay, hopefully that makes sense. And so bringing down the remaining things, this guy becomes 2 to the 3rd power. 2 to the 3rd power is going to be 8 times x squared, and then there's this y to the 3rd power from there, and then this guy, which is the 4th root of x to the 3rd power from there. Good, so let me make it neater. This is just going to be 8x squared y to the 3rd power, and then the 4th root of x to the 3rd power, and that's our answer. Okay, again, lots of different ways to get there, and I am doing more work than that might be necessary just to make sure people are following along. But if you can get to the answer in less steps, that's okay, as long as, again, you show enough steps for someone to be able to reasonably follow along and convince people that that is the answer, right? So your goal is not just to find the answer, but to convince the reader through the work you put down that that has to be the answer. That there's no other way it could be anything else. Okay, so let's see what your author did. Your author did the following. Okay, so your author did not simplify x to the 11/4. So they left it as the 4th root of x to the 11th. They have the 8 and they have the y to the 3rd. So, they just did not simplify the x to the 11/4 power. The instructions should let you know. So far there's no real instructions here as to what kind of answer you want. So when you do your homework, it should give you some information about how they want you to reduce it. So looks like the author just kind of stopped here. Rationalizing denominators into something we call standard form. So it is often useful to eliminate the radical in a denominator by multiplying both numerator and denominator by an appropriate expression. This procedure is called rationalizing the denominator. So if the denominator is of the form square root of a, so again, by default, this means that there's an invisible 2 here. We're just talking about a square root of a. We multiply the numerator and the denominator by the square root of a. In doing this, we multiplied the given quantity by a new form of 1 so that we do not change the value. Right? So for instance, if we were given this 1 over the square root of a and we needed to rationalize it, remember, we're not solving anything, right? We don't have an equation given. So we start with just 1 over root a. And our goal is to come up with a new way to express the exact same thing, but do it in a way where we do not have a square root in the denominator. That's all we're trying to do. Some people get confused in trying to solve this. This is not an equation to begin with. Okay, and so what we want to do is to multiply this by a new 1, right? Multiplying anything by a 1 doesn't change it. And then we want to say, well, this 1 right here, multiplying by 1 doesn't change our original statement. And now this 1 can be rewritten as this, because anytime we have a fraction with the numerator and the denominator both are identical, then that's a new version of 1. We just have to be careful that the denominator is not a 0. Remember, we never are allowed to divide by 0. So a can't be 0 in this case. And so now, if we do this, now the square root of a times the square root of a, these two in the denominator multiply to just give you a, right? This times this equals that, gives you just an a. And now 1 times square root of a, well, that just gives you square root of a. So what we've done is that we've taken this 1 over square root of a, and through this work, we've said that that's equivalent to the square root of a divided by a. All right, well, I mean, it might look more complicated than when we started. It's hard to convince people that we've done anything useful. But what we've done, what we've accomplished is we came up with a way of rewriting the exact same value without having a root in the denominator, right? That's what we call rationalizing. Our goal in rationalizing is not necessarily to simplify or make it neater, make the fraction nicer. Very often the answer gets uglier, but our goal is to eliminate any roots, any radicals from the denominator. Okay, so this is the strategy when we have something of this form, square root of a value in the denominator to start with. We multiply by root of that value divided by root of that same value. On the other hand, if we have a slightly more complicated situation where we have the nth root of m to the n, so note that the denominator in the last fraction contains no radical. In general, if the denominator is of the form the nth root of a to the mth power, where m is less than n, then multiplying the numerator and denominator by the nth root of a to the n minus m will rationalize the denominator. Because for a greater than 0, it is true that the nth root of a to the m times the nth root of a to the n minus m is equal to the nth root of a to the m plus n minus m, which gives you to the square root of the nth root of a to the n, which is equal to a. Okay, what in the world is this saying? Okay, so let me break this down into an example to explain what this crazy thing is saying. So if we have, for example, a situation where we have 1 over the square root of 3, we know what to do, right? This is like the previous example. This is just going to be multiplied by root 3 over root 3. Root 3 times root 3 is going to give you a 3. So this just becomes root 3 over 3, right? This is like the previous example. Now, on the other hand, if we have a slightly more complicated situation where we have the 5th root of 2, for example, we can't just multiply it. We can't just apply the same trick of saying it's the 5th root of 2 over the 5th root of 2, because the 5th root of 2 times the 5th root of 2 does not simplify to give me just the 2 like it does up here, right? Here, the cube root of 3 times the cube root of 3, this gives you 3. Whereas here, if we multiply the 5th root of 2 times the 5th root of 2, that does not equal 2. It doesn't get it out of it. We need 5 copies of 2, not 1 copy, not 2 copies. So this is saying that there's 1 copy of 2 right there. We need more. We need 4 more. And that's what this little summation difference thing here is telling you, the right number that you need. We need 5 minus 1 copies of it. That's what this n minus m situation is. We need 5 minus 1 or 4. We need 4 more. In other words, this number and this number have to add up to that number, right? The 1 and the 4 must add up to 5, because now that's what's going to give you a 2. Okay, so now that will work out. That'll give us a 2 right there. Okay, so if we have 2 to the 4, the 5th root of 2 to the 4th in the denominator, we have to do the same thing to the numerator. Okay, so now this is a new version of 1, so I'm multiplying by 1. And now when I multiply the denominators, the 5th root of 2 and the 5th root of 2 to the 4th, this will just give me a 2 in the denominator. That's what kind of rescues it out of that root. So this will result in a 2 in the denominator, and in the numerator, we end up with the 5th root of 2 to the 4th, we can leave like that, or we realize that 2 to the 4th power is 16. So this is the 5th root of 16 divided by 2. Okay, so a couple more examples. Let's rationalize the first one. The first one's the easy case because we just have an invisible number there. The index is missing, so that means by default is a 2, right? So if we have 2 over root 3, then this is the easy case. All we have to do is multiply it by root 3 over root 3. I know that root 3 times root 3 equals to 3, so this is just going to give me 2 root 3 over 3, and mission accomplished. Now I no longer have a root in the denominator. Okay, for part B, we have 1 over the cube root of 5, right? So 5 to the 1st power. So again, if I just did the cube root of 5, then the cube root of 5 times the cube root of 5, that does not equal 5. I need 2 copies of 5, right? Because 1 copy here and 2 copies there will give us 3. This and this will give us 3 copies of 5. So the cube root of 5 to the 3rd power equals to 5. So that's what will help us unlock that 5 from the denominator. Whatever you do to the denominator, you must do to the numerator. Oh, let's keep the same notation style. Let's write it in green. So let's erase all of this. Write it in green. So okay, so what I'm going to introduce is I'm going to introduce a cube root of 5 to the 2nd power, because I know that's what will unlock a 5 from the denominator. And then in the numerator, this becomes the cube root of x to the 5th power. And so now this becomes the cube root of 5 to the 2nd power divided by 5, which is then equal to the cube root of 25 divided by 5. Good, so there we go. Again, it doesn't look neater or nicer or simpler than the original necessarily, but we've accomplished our goal. We wrote the exact same fraction in a way that doesn't have any radicals in the denominator, right? And that's the goal. Okay, so this one was A, this one is B, so let me put C down here. C, and so we have 1 over A squared, and then we have the 7th root of that. Okay, so this one's tricky. This one is going to be the same thing as the 7th root of 1 divided by the 7th root of A squared. 7th root of 1, well, that's just 1. That doesn't do anything. And now this guy, we're going to have to work with that. A squared, and then we have the 7th root of A squared. So we're going to multiply by a new version of 1, and I want it to be an index of 7 so that they can come together as one big happy 7th root. And then we want a to the power of 7 minus 2, or 5. I need them to add up to 7. Good, so whatever you do to the denominator, you must do to the numerator. So this becomes the 7th root of a to the 5th power. And so now the denominator is just going to be an a value, a, and the numerator, well, there's not much we can do from there, so it just becomes a to the 5th power inside this 7th root. Good, so then there's our answer. All right, let's see what your author did for these questions. So for the first one, just like I did, we multiplied by root 3 over 3, a new version of 1. The denominators become 3, so end up with 2 square root of 3 over 3. For the second one, again, very important to notice that we multiplied it by the appropriate value here. So there's the cube root of 5 to the power of 1, 5 to the power of 1. So we needed 2 more to get to 3. So then this, the cube root of 5 times the cube root of 5 squared gives you a 5. And in the numerator, there's not much you can do, so you leave it alone. And then finally, same thing, the 7th root of 1 is 1. The 7th root of a squared, good. And so now we multiply it by the appropriate power and that unlocks an a in the denominator, which gives us this guy. Okay. Hopefully that is enough to help you finish your homework. Please feel free to drop by my office hours if you have any questions.